Welcome to all of you. Now we discuss about the question paper 2024, paper DSCC-2, Group A, Basic Algebra for semester 2 under CCF, University of Calcutta, 4-year B.Sc Mathematics Honors, MTHM. This question paper 2024 MTHM, and the equation whose roots are squares of the roots of the equation x to the power 4 minus x cubed plus 2x square minus x plus 1 equal to 0. Let alpha, beta, gamma, delta be the four roots of the given equation x to the power 4 minus x cubed plus 2x square minus x plus 1 equal to 0. We have to find an equation whose roots are alpha square, beta square, gamma square, and delta square. Let y equal to alpha square. Since alpha is a root of the given equation, then from the equation 1 we can write in place of x, we can write alpha to the power 4 minus alpha cube plus 2 alpha square minus alpha plus 1 equal to 0. Now, putting y in place of alpha square by 2, this. So, alpha to the power 4, we can write alpha to the power 4. So, we can write alpha square whole square. So, this equals to y square. So, we write alpha to the power 4 equal to y square. Alpha cube, this equals to alpha square into alpha. So, this alpha square is equal to y into alpha. This is equal to y into alpha, and so on. So, this y square plus 2y plus 1 equal to alpha bracket y plus 1. Squaring on both sides, we get this. After simplification, we get this equation y to the power 4 plus 3y cube plus 4y square plus 3y equal plus 1 equal to 0. This is the decode equation whose roots are alpha square, beta square, gamma square, and delta square. Next question, 1b. If Sn equal to this 1 plus 1 by 2 plus 1 by n, then prove that Sn greater than twice n whole divided by n plus 1 if n is greater than 1. Consider n positive numbers 1, 1 by 2, 1 by n, and then using arithmetic mean and greater than harmonic mean for all non-equal positive numbers. So this is the arithmetic mean, sum of the all numbers divided by whole number of total numbers n is greater than n, and divided by 1 by 1 plus 1 by 1 by 2. So this is equal to 2 and so on if n greater than 1. So this equals to sum of natural numbers. This is equal to n into bracket n plus 1 all divided by 2. So we get Sn is greater than twice n by n plus 1. Next, find the general value of I to the power I. First, we find the polar form of this I. This modulus of I is equals to 1, and this I, argument for this point I is pi by 2. So general argument, this pi by 2 plus twice k pi, where k is any integer, 0 plus minus 1 plus minus 2 and so on. Therefore, the general polar form of the complex number I is equal to e to the power I bracket pi by 2 plus k pi, where k is any integer. For a complex number z and a complex exponent w, the general value of z to the power w is given by the formula z to the power w equal to e to the power w log z. Note that this log start with the capital L. Actually, this is the general value of the complex logarithm function. That is a multi-valued function. This multi-valued function log z equal to ln modulus z. Actually, this is the log to the base e. This is real value modulus z plus I. Argument of z. This argument starting with small a. This is the general value of argument of z. So I to the power I, we have z equal to I, w equal to I, the general logarithm of I is this log of I. This is equal to ln modulus of I plus I bracket pi by 2 plus twice k pi. Modulus I is 1, k belongs to capital Z, any integers, log 1 0, 0, and so we get this. Now we substitute this into the exponential formula. I to the power I equal to e to the power I into log I, starting with the capital L, general valued logarithm of the complex number I. So this log I equal to this. So put this value, we get e to the power I square bracket pi by 2 plus twice k pi. This I square minus 1. So the general value is this, and where k belongs to the set of all integers Z. The general value this, and the principal value for this I to the power I put k equal to 0. So we get e to the power minus pi by 2 for the principal value of I to the power I. And this is the log multivalued function. This k belongs to all integers, and the principal value is this e to the power w equal to the power w log z. This start with the small letter L. This log z is the principal value of the capital log this z multivalued. Actually, this argument of z is starting with the small letter a, and this argument of z starting with the capital letter A. This capital letter argument z is the principal value, and this small letter starting with small letter a, this argument is general value multivalued. This argument of z is theta is the principal value for the corresponding to the k equal to 0, and for many valued function argument of z theta equal to twice k pi. K belongs to the set of all integers. Next question 2a. Show that the product of the all values bracket root 3 plus I whole to the power 3 by 5. First we write this root 3 plus I in modulus argument form. This modulus of this 2, and argument is this pi by 6, and general argument of this pi by 6 plus twice k pi. K belongs to set of all integers. So this 2 into e to the power I pi by 6 plus twice k pi. K belongs to set all integers z, capital Z. We now find the value z to the power 3 by 5 using the general polar form. This z to the power 3 by 5, 2 e to the power I bracket pi by 6 plus twice k pi whole to the power 3 by 5. So 2 to the power 3 by 5 is this, and we get 5 distinct values for different k's, k equal to 0, 1, 2, 3, 4, 5. So z to the power 3 by 5, from this z to the power 3 by 5, we get 5 different values, complex value function, this for corresponding to k equal to 0 to 4. Now this product, we want to find the product of this. This is the product of the all values of this. All values of this. We want to find these 5 product of the 5 complex numbers. So this capital pi k equal to 0 to 4. This means this capital pi equal to 0 to 4 ai. This means a1 dot a2 dot a3 dot a4. So this 2 to the power 3 by 5 whole to the power 5, this equals to 8, and some of these arguments, and this pi by 10 plus 6 k pi by 5 k equal to 0 to 4. So we get this 25 pi by 2. The principal argument is found by subtracting the multiples of twice pi. So this 25 pi by 2, this we can write 25 by 2 equal to 12 pi plus pi by 2. So actually the principal argument is this pi by 2 for this. So effective principal argument is pi by 2. The product P this product is p, this p, actually this 8 into e to the power I pi by 2. This 8 from this to the power 3 by 5, from this 8 whole to the power 5 is 8, and from this we get this e to the power pi by I pi by 2. Now using Euler's formula, e to the power I theta equal to cos theta plus I sin theta. So 8 cos pi by 2 plus I sin pi by 2 is equal to cos pi by 2 0 and sin pi by 2 equal to 1. So this is equal to 8 pi. So required product is 8 pi. Next question 2b1. So that the ratio of the principal values 1 plus I whole to the power 1 minus I and 1 minus I whole to the power 1 plus I is sin log 2 plus I cos log 2. Now we first find the principal value of 1 plus I whole to the power 1 minus I. By the previous formula, this z to the power w equal to e to the power w log z. This is the principal value of this complex function z to the power w. Z is complex number, w is also complex number, another complex number. So log z equal to ln mod z plus I, principal value of argument z. Now for the base means here this 1 plus I, and the exponent is 1 minus I here. This w is equal to 1 minus I, and base z is this 1 plus I. So modulus of this base is root 2, and the principal argument is this 1 plus I. 1 plus I in the complex diagram plane, actually this position 1 1. So this position 1 1 in the complex plane, and this is the x-axis, this is the y axis. This is the point 1 plus iy complex plane. Sorry, I1, I. This is the 1 plus I. This is the 1 plus I. So this origin coordinate 0, and this 1, this point is 1, 1, 0, and this point is 1, 1. So join this origin and this point 1, 1, 1 plus I actually in 1, 1. So this from the positive x-axis in anticlockwise direction, angle is pi by 4. So for this 1 plus I, the principal argument is this. For this principal argument of this is z 1 plus I. This equals to pi by 4. This is the pi by 4. And this, so we write pi by 4, and principal value of the logarithm is this log 1 plus I, this starting with small a. So this is the principal value of multivalued logarithm function, and this is equal to ln root 2 plus I pi by 4, and this equal to half ln 2 plus I pi by 4. The principal value of the expression is this 1 plus I whole to the power 1 minus I, and this is equal to this, and substituting this value, and after simplification we get e to the power 1 by 2 ln 2 plus pi by 4 into e to the power I bracket pi by 4 minus 1 by 2 ln 2. Similarly, we can find the principal value of 1 minus I whole to the power 1 plus I. So we get this. Now calculate the ratio of the principal values. So this by this, and so e to the power this into this, into e to the power I into this, e to the power this into I into this, cancel this. So e to the power this into this. So e to the power this minus this, taking common I. After simplification, we get e to the power pi by 4 plus pi by 4. So this pi by 2, and this equal to the power I bracket pi by 2 minus ln 2. Now using Euler's formula, e to the power I theta equal to cos theta plus I sin theta. This e to the power I into this, so cos of this plus I sine of this. Now using the trigonometric identities, cos of pi by 2 minus x equal to sin x, and sin pi by 2 minus x equal to cos x. So we get sin ln 2 plus I cos ln 2, and this is the required ratio is sin ln 2 plus cos ln 2, I cos ln 2, and this is the ratio. of this principal value of this and this. Next question, find the principal value of the argument z where z equal to 1 plus I tan 3 pi by 4. Now the complex number z equal to 1 plus I tan 3 pi by 4. The real part is x, this 1, and the complex part is imaginary part is this iy, x plus iy. So y is this tan of 3 pi by 5. First, we determine the quadrant of z. Now, this 3 pi by 5 lies between pi by 2 less than 3 pi by 5 less than pi. So, this 3 pi by 5 lies in the second quadrant, where the tangent function is negative. Obviously, all sine, tan, cos. So, second quadrant is all sine, tan, cos. First quadrant all positive. Second quadrant all sine positive. So, and second quadrant tan is negative. So y equal to tan 3 pi by 5 is less than 0. The real part x equal to 1 is greater than 0. So x positive, y negative. So in the complex plane, x positive, y negative. So this complex number x positive, y negative. X axis is the iy axis, and this is the x positive and y negative. So this point lies in the fourth quadrant. This first quadrant, this second quadrant, third quadrant, and this is the fourth quadrant. So this complex point lies in this x, comma y. This y is negative, this y is positive. So this y is negative. So this plane is this. So obviously, this argument in this way, this minus, because this positive x-axis is the clockwise sense. So this angle is minus theta. This angle is minus theta. So complex number is the positive real number and negative imaginary part lies in the fourth quadrant. The principal value, the argument, that is the argument of z, principal argument of z for a number of the fourth quadrant in the range minus pi by 2 to 0, minus pi by 2 to 0, because minus pi by 2 to 0, minus pi by 2. So from this to 0, from this minus pi by 2 to 0, this minus pi by 2 is this line on this line, and this line 0, angle is 0. And so principal argument of z is equal to tan inverse y by x. So here y is tan 3 pi by 5 and x is 1. So we get this tan of this. Now we know that tan pi by theta equal to minus tan theta. So tan 3 pi by 5 equal to, we can write tan of pi minus 2 pi by 5. This equals to minus tan 2 pi by 5. Substituting this into the expression, principal argument of z is equal to tan inverse minus tan 2 pi by 5. Using the property tan inverse minus u equal to minus tan inverse u. So principal argument of z is this minus tan inverse tan of twice pi by 5. So this equals to minus 2 pi by 5, principal argument of z. So this the answer, minus 2 pi by 5. Next question 2c, using Cauchy-Schwarz inequality so that x1 square y1 plus x2 square y2 plus dot dot xn square by yn greater than equal to x1 plus x2 plus xn whole square whole divided by y1 plus y2 plus yn. x1, x2, xn are real numbers and y1, y2, yn are positive real numbers. Applying the above result, prove that this greater than equal to 3 by 2 ABC are positive real numbers and ABC equal to 1. Now, Cauchy-Schwarz inequality states that for two sequences of real numbers a1, a2, dot, dot, an, and this b1, b2, bn, following holds, this summation ai I equal to 1 to n ai bi whole square is less than equal to summation ai square into summation bi square. Set ai equal to xi by square root of yi and bi equal to square root of yi, I equal to 1 to up to n. Substituting these into this inequality, we get, put this ai equal to xi by root yi and bi equal to root yi, ai square is this and bi square equal to this. So cancel root yi and this whole square. So we get this, and dividing on both sides by summation of yi, which is positive, we get, and this, which is the, actually this, if we expand this, we get this expression is this. We get this x1 plus x2 plus xn whole square whole divided by y1 plus y2 plus yn. Actually, this is the, here the right hand side is there, here is the left hand side. Actually, this is less than equal to, and this is the greater than equal to sign. So these are same, which is the required inequality. Second part, now we expression E, set the expression E 1 by a cube b plus c plus dot 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 dot. This is. Now we write this first term to match of the form xi square by yi. So we can write this 1 a square 1 by a cube. So we can write this 1 by a whole square whole divided by a bracket b plus c. After simplification, we can find this 1 by a cube bracket b plus c. Next, put here n equal to 3. Here the numbers, n numbers. So here only for 3 numbers. And 3 numbers, x1 is 1 by a1, x2 is 1 by b, and x3 is 1 by c. And y1 is a plus bracket b plus c, y2 b bracket c plus a, y3 c bracket a plus b. So E is greater than equal to this, because E equal to this, and so E equal to this is greater than x1 plus x2 plus x3 whole square divided by y1 plus y2 plus y3. So applying this, we get this. Now we simplify the numerator and denominator separately. Numerator is this, 1 by a plus 1 by b plus 1 by c whole square. After simplification, we get a b plus bc plus ca whole square, because giving that a b c equal to 1, a into b into c equal to 1. So denominator is ab plus ac plus bc plus ca plus denominator is this ab bracket c, b bracket c plus a, c bracket a plus b. So simplification, we get this 2 into bracket ab plus bc plus ca. Substituting this back into the inequality, we get cancel each other, ab plus bc plus c not equal to 0. So E is greater than this. Now using the arithmetic mean geometric mean inequality for ab bc ca. So this is the arithmetic mean ab plus bc plus ca whole divided by 3 greater than equal to this cube root of this AB into BC plus BC into CA. So this is equal to a square p square c square whole to the power ABC equal to 1. So this is equal to 1. Now, so this AB plus BC plus C is greater than 3, because this is greater than equal to 1. So we get this is greater than equal to 3 by 2. So this expression E is greater than equal to 3 by 2. This completes the proof. Question 2D. Obtain the equation whose roots are the roots of the equation 4x cube minus 8x square minus 19x plus 26 equal to 0, each diminished by 2. Use Descartes' rule of signs to both the equations to find the exact number of positive and negative roots of the equation. Now we have this equation, this from this left hand side, this expression polynomial in x, we say this is the fx. So this, let fx equal to this. Now let a alpha beta gamma be the 3 roots of this cubic equation. This we have to find the equation alpha minus 2, beta minus 2, gamma minus 2, because here this we have to obtain the equation the roots are the roots equation each diminished by 2, because diminished by 2. So this is the alpha minus 2, beta minus 2, and gamma minus 2. Let y equal to alpha minus 2. So obviously alpha equal to y plus 2. Now alpha is a root of this given equation. So 4 alpha cube minus 8 alpha square minus 19 alpha plus 26 equal to 0. So put alpha equal to y plus 2. So 4 bracket y plus 2 whole cube minus 8 and so on is equal to 0. Let phi capital Y, where capital Y equal to small y plus 2. So obviously this above expression, this phi capital Y, this 4 capital Y cube minus 8 capital Y square minus 19 capital Y plus 26. Just simple transformation using this y capital Y equal to small y plus 2. Now we express this expression phi y polynomial in the expression capital Y minus 2 by the method of synthetic division. That ordinate scheme. The scheme is this: the coefficient of this expression, polynomial expression 4, and this minus 8, this minus 19, and this 26. If if there any term is absent here, say suppose this minus 19y is absent, so we put here 0 here. So this put all coefficients with sign, complete y cube, y square, y, and constant. Or if any one of this term is absent, and then put for this absent term put 0 here. Now for this expression, one to expression, this polynomial expression in the expression factor of this polynomial expression as a polynomial of y minus 2. So for expression of this expression, polynomial expression in the y minus 2, so we have put here 2 here. If y minus y plus 2, if we want to express this polynomial in y plus 2, then put here minus 2, because y minus of minus 2. But here y minus 2, so we put here 2. Now, first coefficient of y cube, this 4, just down arrow by this 4. And 4 into 2, 8. So put here 8. 8 minus 8 is 0. Sum this 0. 0 into 2. 0 into 2 is 0. This put here 0. Now minus 19 plus 0 is minus 19. 2 into minus 19 minus 38 is here. And 26 minus 38 minus 12. And separate this term. This is the if we divide this polynomial by this polynomial y minus 2, then we get the remainder is minus 12, and this the remainder, and this is the quotient 4 y square and 0 y minus 19 the quotient after dividing this polynomial by y minus 2. Next, this 4 is 4 same, and 4 into 2, 8, put here 0 plus 8, 8, 2 into 8, 16, and add this minus 19 plus 16, this is minus 3, and this is the residue in the dividing by this polynomial with y minus 2, and this residue, separate this residue this here. Next, 4 is 4 here, 4 into 2, 8, 8 into 8, 8 plus 8 is 16, separate this residue in this stage, and lastly 4. So the all residues are this minus 12, minus 3, 16, and 4. So phi capital Y equal to minus 12 plus minus 3 into y minus 2 plus 16 into y minus 2 whole square and plus 4 into y minus 2 whole cube. Next, capital Y, put here capital Y equal to small y plus 2, put here small y plus 2. So if we put y capital Y equal to small y plus 2, so cancel plus 2 minus 2, so small y here. So minus 12 minus 3y plus 16y square plus 4y cube. So this expression, this 4y plus 2 whole cube and this equal to 0 simply reduces to this expression, this minus 12 minus 3y plus 16y square plus 4y cube, that is 4y cube plus 16y square minus 3y plus 12 equal to 0. And this is the required equation whose roots are diminished by 2. If the roots of this equation is alpha, beta, gamma, then roots of this equation are alpha minus 2, alpha minus, gamma minus 2, beta minus 2, and this. Next, we find the number of roots of this equation by Descartes' rule of sign. First equation expression, given expression is this 4x cubed minus 8x square minus 19x plus 26, and this an equation of degree 3. So it must have the exactly 3 roots, real or complex roots. Now, sign of these coefficients, this plus, minus, minus, and plus. So this is the only this is the change. This is the one change, and this 2 change. So we get the number of variation of signs in fx is 2. Is 1 plus 2 minus and minus 2 plus. So 2 changes here. There, then the number of positive roots fx is equal to 0 is either 2, because there are 2 changes, variation of sign 2, or is diminished by the even number. So 2 minus 2 is 0. So either 2 or 0, minus either 2 or 0. Now f of minus x, put here f of minus x, so 4 minus x whole cube minus 8 minus x whole square minus 19 minus x plus 26. So this is equal to this. And the sign of the coefficients of this minus, minus, plus, plus. So we get only one variation of sign, minus to plus here. So number of negative roots of the equation f x equal to 0 exactly 1. So all combinations of the roots of the f x equals to 0 is positive roots either 0, negative roots always 1, and the equation is third degree polynomial. So 3 roots. So other 2 roots from complex. So total number of roots is 3. If number of positive roots is 2 and negative root is 1, and complex roots must be 0 and total number of roots 3. Next, the transformed equation gx. For this transformed equation is this 4y cube plus 16y square minus 3y plus 12 equal to 0. For this transformed equation, this coefficient of this plus, plus, minus, minus. So we get only one changes of sign, this. So number of positive roots in gx equal to 0 equal to 1. And the g of minus x equals to minus, plus, plus, minus. So there are 2 changes. It is minus to plus and plus to minus. So we get there are 2 changes here. So negative roots in gx equal to 0 either 2 or is decreased by even number. So 2 minus 2 is 0. So all possible combinations of the number of roots of gx equals to 0. Number of positive roots 1. 1 is always 1. Positive roots always 1. And negative roots is 0, maybe 0 or maybe 0 or this. So total number of roots is 3. So complex roots 2. Next, positive roots must be 1 always, and negative roots is 0. Negative root is 0. Negative roots is 0. Sorry, 1, either 2. So negative root is 2. Sorry, here it is 2. It is 2, not 3. It is 2. 2 plus 1 equal to 3. 2 plus 1 equal to negative roots 2 and complex root in this case 0. Next question 2E1. Find the relation among the coefficients of the equation ax squared plus 3bx squared plus 3x cx plus d equal to 0, where a not equal to 0, if its roots are in geometric progression, a, b, c, d are real numbers. First, the given equation is this. Since the roots are in geometric progression, so this is the technique to choose the roots in this way: alpha by beta, alpha and alpha beta. Is the very important for when the cubic equation, when the roots of the cubic equation are in GP, geometric progression, you must have to choose this alpha by beta, alpha, alpha beta, because geometric progression alpha beta into alpha, sorry, into beta, common common factor is beta, this common ratio, alpha beta into beta is alpha, alpha into beta, alpha beta. From the relation between roots and coefficients of the equation, the sum of the roots alpha beta plus alpha beta is equal to minus this by this, minus the coefficient of x square by coefficient of x cube. So this, and the sum of the product of the 2 roots at a time is alpha beta into alpha plus alpha beta into alpha beta plus alpha into alpha beta. So this is equal to coefficient of plus into coefficient of x divided by coefficient of x cube, 3c by a. And product of 3 roots alpha beta into alpha beta, this is equals to constant term minus into constant term and divided by coefficient of x cube. Actually, this relation is redundant for this problem. From the second relation, we get this taking common alpha. So we get alpha by beta plus alpha beta equal to 3c by a. Now this alpha by beta plus alpha beta we get from this first relation minus 3b by a put here. So alpha equal to minus c by b. Now alpha is the root of the given equation. So we can substitute alpha in place of x. So a alpha cube plus 3b alpha square plus 3c alpha plus d equal to 0. This now put the value of alpha minus c by b here, and after simplification we get b cube d equal to a c cube, and this is the required answer. Actually, the third relation is redundant here. Next question, 2E2. Apply Sturm's theorem to find the number of real roots of x cube minus 3x plus 2 equal to 0. Now here the function fx equal to this. Then the first derivative with respect to x, 3x square plus minus 3 equal to this, taking common the constant term 3, x square minus 1. Deleting the constant 3, we get this expression x square minus 1, and say this is the first second term function, this fx equals to f1x equal to x square minus 1. Dividing fx by f1x. So fx is this and f1 is x this. We get this is the quotient, and this is the remainder, this minus 2x plus 2. From this remainder, taking the constant term 2, not minus 2, taking common only 2, and deleting the constant, and then multiplying by minus 1. And this is the important rule for this Sturm function. Multiplying by the minus 1 for each division of this. Choose f2x equal to x minus 1. Again, dividing f1x by f2x, so we get this, and this is the residue is 0. So this is the very important case. Since the remainder is 0, and this establishes that the given equation has multiple roots. And we stop here. The last non-zero polynomial f2x. So the Sturm's functions are given by fx is this, f1x is this, f2x is this. And from the following table, we observe that this is the variation at infinity, this minus infinity, 0, infinity. So fx, the fx function is this x cube minus, so this is the fx is this, fx is x cube. So the highest degree term x cube. So actually minus infinity means the large negative number, say minus 100. So minus 100 cube. So this is the negative value. So we put here fx is negative value. Dominant value is this negative value. So put here negative. f1x, this x square. So minus 100 square. Minus 100 square is this positive value. So this is the positive value. Dominant term is positive value. This positive value. And minus infinity for f2x, this is equal to obviously minus infinity minus 100. So this is negative value. So we get one variation, two variation. So changes of sign is 2 here. This is the v of minus infinity is 2. And for 0, put x equal to 0 here. So fx equal to 2, this positive. So this positive. f1x equals to this minus 1, this minus. And f20 equal to minus 1, this minus. So we get only one variation. Changes of sign is 1. And for infinity, for large positive value, this f of 100. So 100 cube. So this 100 cube positive value is positive, and 100 squared is positive, and this 100 is the positive. So there is no variation of this in this sign of this. So we find for this, it is 2 and 1. So variation of sign is this 1 from negative sign to 0. So this v minus 2 to v minus 0, difference actually the sign, difference of this sign changes is 2 minus 1. This is not negative sign, actually difference between this sign. So 2 minus 1 equal to 1. So v denotes the number of sign changes in the sequences. So there is only one variation of sign from minus infinity to 0. So number of negative root is 1 in fx equals to 0. So number of negative roots is here 1. Now v0 to v infinity sign changes is 1. So there is only one variation of sign from 0 to infinity. So number of positive roots is 1. The equation has two distinct real roots, but one of them is double root. Therefore, all roots of the equation are equal. Actually, if we express this x cube minus 3x plus 2, we can write this x plus 2, x minus 1 whole square. Actually, there are three roots, minus 2, 1, 1. So this 1 is the double root. So actually, two distinct root is -2 and 1, but 1 is here double root. 1 is the double root. X cube minus 3x plus 2. Actually, you can draw this x cube minus 3x plus 2, x cube x cube x cube minus this x plus 2 x minus 1 whole square. So this is the question. Next question 2f. By Faraday's method, solve the equation 2x to the power 4 plus 6x cube minus 3x square plus 2 equal to 0. Now, first we multiply by 2 with the given equation, because actually 2x to the power 4. So if we multiply by 2, so this 4x to the power 4. So 4x to the power 4, then this can be written as 2x square whole square for this term, first term, 2x square whole square. So for this is a technique. So if there is no constant is here, so only x to the power 4 need not to any multiply by any constant. But if this constant is 2, so if we choose to multiply in such a way that so that this term 4x to the power 4 a complete square term. So this 2x square whole square, this 2x square whole square. Let this 2x square plus 3x plus lambda whole square minus mx plus n whole square equal to 0, where lambda, mn are constant. This is the equation 2. Simplifying this 2, we get this x to the power 4, x cube, this x square, this x, this constant term. And comparing with this, actually 12x to the power 4 plus 12x cube are same. So we choose this equation 2 in such a way that this x to the power 4 and x cube term are same. So this same. So only the coefficient of x square is this. So here coefficient of x square is -6. So this is equal to -6, and this coefficient of x is this. So here coefficient of x is nothing. So actually this is the 0. This is the 0, and the constant term is 4. So here constant term is lambda square minus n square. This is equal to 4. So we get this m square equal to 15 minus 4 lambda, and mn equal to 3 lambda, and n square equal to 4 lambda square minus 4. These 3, 4, and 5 equations. Squaring this equation 4 and using 3 and 5, we get m square n square equal to 9 lambda square. Now m square equal to this and n square equal to this. From 3 and 5, put these values of m square and n square, and simplifying, this is the cubic equation in lambda. Now we want to solve this cubic equation of lambda 6, but it is very difficult. Cardan's method, we not apply here Cardan's method. We apply here there another technique is lambda equal to 5 by 2 is the root of this equation, but why? Actually, we technique is this lambda 2 lambda cube plus 3 lambda square plus 8 lambda plus minus 30 equal to 0. So multiply by this 4, this equation 4. Actually, this 8 lambda cube, so we can write 2 lambda whole cube. So we multiply here 4. So this 2 lambda whole cube. Actually, we want to put this t equal to 2 lambda. So after putting t equal to 2 lambda, we get from this equation t cube plus 3t square minus 16t minus 120 equal to 0. Now we find the positive factors of 120. And these are positive factors are these 1, 2, 3, 4, 5, 6, 8, and this. Now we put all terms, all positive factors, positive divisors, this here, and which positive factor satisfy this equation. And after checking this, first t equal to 5, if we put here t equal to 5, then we get identical equal to 0. This term is the 0. So t equal to 5, that is t equal to 5 means lambda equal to 5 by 2. So we use this technique here for choosing the lambda 5 by 2. It is not so easy to choose the lambda equal to 5 by 2. Now, choosing this value of lambda, so from question 3, m square equal to this putting lambda equal to 5 by 2 and lambda equal to 5 by 2, n square equal to, so m equal to plus minus 5 and n square equal to 9 by 4 and n equal to plus minus 3 by 2. Now, mn equal to 15 by 2, mn equal to 3 lambda, so 5 by 2 and 15 by 2. So either mn is positive. So m and n are both separately positive because this m into n equal to positive value. So m equal to 5, n equal to 3 by 2, or m equal to minus 5, n equal to minus 3 by 2. Either same sign, either positive sign or negative sign, both the values of m. Taking m equal to 5 and n equal to 3 by 2. So equation 2 is this, from 2, put m and n and lambda, we get this equation 2 from this to this. This is the expression is this. And after simplifying this, this into this equal to 0. After simplifying this, actually is a square minus b square, a plus b into a minus b. And using this formula, you can easily simplify this: a square minus b square, a plus b into a minus b, and this. So from the first factor, x square plus 4x plus 2, we get by formula minus b plus minus root over b square minus 2a whole divided by b square minus 4a c b square minus 4ac by 2a. So we get this minus 2 plus minus root 2, and from the second term we get x equal to half bracket 1 plus minus I, and so the required roots are this and these 4 roots of this. Very simple. No, I am sorry. This must have hanging here. This must have. So thank you for this complete this solution of the group A DSCC paper 2. Thank you.